Hey guys, what's up? Welcome to another video of CHE 101, and today we will be talking about the variable volume batch reactor, which is one of the topics in chemical reaction engineering and kinetics, or REACCHE. So let's begin. So here are the important equations to remember. So you may pause this video to view these equations. So we will be using these equations in solving the next problems. Okay. So let's head to the first problem. So we have here a gaseous reaction carried out in a constant pressure and constant temperature batch reactor with uh, the feed containing 20% inert. And then after some time, the reactor has expanded to a volume 1.284 times larger than the starting volume. So we are to determine the concentration of A after 20 minutes, assuming the gases behave ideally. And here is the solution. Okay. So we have here the given information from the problem, and then we have here the required or the unknown quantity, which is the concentration of A at 20 minutes. Okay. So how do we solve this problem? We need the concentration, and if we look back at the list of equations, we have that, this one. So we're going to use this equation. So let's write that down. Ca equals CaO times 1 minus x all over 1 plus epsilon x. Okay. We don't know CaO, we don't know x, and we don't know epsilon yet. So how are we going to proceed? We can derive these values from the given information. So let's start with CaO. So we know that the gases behave ideally as stated here. So we can use the ideal gas equation, PV equals nRT. But how do we incorporate CaO here? So we can rearrange this equation in such a way that we know that C is a concentration. So that's moles over volume. So we can rearrange this in this manner. Okay. So our N over V here becomes now the CaO. Okay. Then we have values for pressure and temperature as given here, and then R is the gas constant. So we can now solve for CaO. So CaO is going to be this one. Okay, so 4.9236 atmospheres all over the gas constant. So that's the 0.08206. And then our temperature is at 300 Kelvin. So solving for CaO, you should get 0.2 moles per liter or 0.2 molar. So we're done with CaO. Let's now try to solve for epsilon. Epsilon is the number of moles of products minus moles of reactants all over the moles of reactants times the quantity 1 minus inert, or this is the fraction of all of the reacting species. Okay. So in this case, our product contains 3 moles. Our reactant contains 2 moles all over reactant again, so that's 2 moles times the quantity 1 minus the fraction of inert, so 20%, that's 0.2. So you should get 0.4 for the fractional change in volume epsilon. So all we need now to find is x, the conversion. And we can relate the conversion in terms of the change in volume and the epsilon. So that's V minus V naught all over epsilon V naught. And then we know that V here is related to our initial volume, S1. So we can make use of that. So 1.284 V naught minus V naught all over our epsilon is 0.4 here, V naught. We can cancel the V naught. So this becomes 1. So this equation becomes 0.284 over 0.4, and that's going to be 0.71. Okay. This is draw a line to separate the derived quantities from the actual solution. Okay, we now have values for CAO, epsilon, and X, and now we can proceed to solve the equation. So substituting the values, okay, you should be able to get Ca to be 4.517 times 10 to the negative 2 molar. And that's our final answer for the first problem. Okay. And now move to the second problem. Okay, this is from Chemical Reaction Engineering, the third edition by Levenspiel. So in the original problem, we're only asked to find the first order, but let's try to use the other equations too. So let's try to find the zeroth order, first order, and second order rate constants for this reaction given the following information. So let's write down the given. So we have the reaction, and then we have the change in volume in the specified time. And then it was stated that the reactor contains 80% A. So we can assume that the remaining component is or are inerts. Okay. And then again, it's a constant pressure reactor. So we can assume that only the volume is being varied. Okay. So we solve first for the zeroth order rate constant. If we go back, these are our equations for the integrated rate laws. So we will use these. Okay. But before we proceed solving, let's already look for the values of epsilon and the value of x. Okay. So for epsilon, that's just the moles of product minus moles of reactant all over moles of reactant times 1 minus inert, or in this case, we can directly use 0.8. Since 1 minus inert refers to the fraction of moles of the reacting species. Okay. So you should get epsilon be negative 0.4. For the conversion, that's V minus V naught all over epsilon V naught. We can write this one as the change in volume. Okay. And we know that the volume decreased by 20%. So that's going to be 0.2, but we put a negative sign because it decreased. Okay. And then let's substitute now the value for the epsilon. So that's negative 0.4 V naught. So simplifying, you should get 0.5. Okay, we now have epsilon and we now have x. So we can now proceed in writing or in solving for the zeroth order rate constant. So the integrated rate law for zeroth order is this equation. Okay, let's just separate this again. Okay, here. Equals KT. Then we now substitute the values. So that's going to be CAO, since we don't have a specified value for CAO, over the epsilon, which is negative 0.4, ln of 1 plus epsilon, negative 0.4, x 0.5 equals K, and then T, which is 3. So simplifying, you should get K for the zeroth order to be 0.186 CAO. Then since this is zeroth order, the unit is molar per minute. Okay. This is now our answer for the zeroth order rate constant. Let's now proceed to the first order rate constant. We already have a value for our epsilon, so we just copy that, as well as for our x. Okay. Then we just write the equation for the first order, which is ln of 1 over 1 minus x equals kt. So we substitute values. Okay. Then we solve for k, and you should be getting 0.231. And then since this is first order, okay, this is first order, the unit should be in per unit of time, or that's per minute. And this is our answer for the first order rate constant. Okay. Finally, we do the second order rate constant. So again, we copy the epsilon and the x, okay, and then we substitute values at the right side. So for the second order, the equation is 1 plus epsilon times x over 1 minus x plus epsilon ln of 1 minus x equals k CaOT. Okay. We substitute the values. So this is going to take quite some time because it's a long equation. We're almost done. There. And then now solving for k, you should be getting 0.2924 over CaO since we don't have an exact value for the CaO. And then since this is second order, oops, I forgot to write it again, k second, the unit should be in liters per mole minute or per molar per minute. Okay, so we have now answered all of the required quantities. So in this video, we learned the different equations to be used in variable volume batch reactor problems and how to properly use these equations. So I hope you learned something, guys. Thank you.